Okay, so let's go back to that problem that I kind of messed up there, but only a little mess up, about 10 seconds worth. So, and we were doing this physics problem, and we're given the equation. We launched this rocket straight up in the air, and it follows this equation. So that's the time versus what position? T's time, S is the height, T's in seconds, and S is in feet. And we found the average rate of change from 1 to 3. So before we go on any farther, let's look at this as an animation. So here I've drawn a GeoGebra drawing animation here, and I know it's a little faint there. Can you see that green line in the back there? Mark? Was it Mark? No? In the back row there, Mark? Can you see that green line there? Yeah. So don't anybody fall asleep. That's like the biggest I can make it. Everybody see this green line right here? And that's the line of travel. Here's my particle A. So let's put A into motion real quick. And so let me put it into motion. Hang on, I want to do one more thing before I do that. I want to make my settings so it only goes in one direction one time. We're going to have this rocket going up and down a bunch. All right, so let's put it in motion. And now I want you to look at its speed. Now, speed and velocity are basically the same thing. Speed is always positive. Velocity can be positive or negative depending if you're going forward or what, backwards. But they're closely related. We'll see that as we work through the semester. So there's that particle in motion. Is it speed the whole time? No. You notice when it started kind of fast, didn't it? And then it slows down and then turns around. So that means its velocity change sign and comes down, and then it starts accelerating back up. So let's put it in motion one more time. Oops. Got to reset the slider. So it's definitely changing its velocity. And because it's changing its velocity, its average velocity should change as well. Now, as it gets launched, it's going fast, right? Because it has that initial boost. So it's already slowing down. What's causing it to slow down again? Gravity and a little air resistance, but the model ignores that. And so its average velocity is going to be faster down here than up there as it's going up. And then what happens is average velocity is actually going to be faster again, lower when it's coming back down, because it's picking up speed as it's getting ready to hit the ground. Okay, now let's go ahead and show you what this would look like. Here's the height plotted versus time, and I'll go ahead and put a second point on there, and let me reset everything. So this is just height versus time. So actually the motion is up and down, but what do we tend to do? We tend to look at it as a function in two variables, and that's why it tends to look like this here. Hit play. All right, so for us, we have to understand the calculus of how that's changing. So that's what we're going on today. So let me flip the lights back on, and let's go through that mistake I made last time. It's a minor little mistake. Who are my computer science people in the room? Just one? Wow. Well, what's one of the most important things in computer science? To know what your variables are, right? You got to know what your variables represent. So let's go back through. Oops, let me turn this back on here. Get my stick back out. All right, so let's go back through. We found this average rate. How did we find that average rate again? We used this formula here, which is a lot like the slope formula. Difference in the y's over the difference in the x's. That's that slope formula that you studied in high school is one of the most important formulas we look at in mathematics, especially in early part of calculus. And so it's the slope of what we call a secant line. And then what's going to happen is we're going to start moving this closer and closer and closer to what happens till we get what's called a tangent line. That's where we're going. So we found the average from here. We found it to be 32 feet per second. And then we did from 1 to 2, and we found that to be 48 feet per second. So this is all stuff we did last class. Then we did from 1 to 1.1, and we came up with it being 62.4. Notice that average velocity, average speed is going up. Why is it going up? Because we're looking at a smaller time interval, closer to when we launched the rocket. That's why that average velocity, because we're looking at a tighter window, and that rocket was going faster in that tighter window. And then, how fast is it traveling? Exactly at 1 second. So what did we do? We said, I'm going to look at the interval 1 to 1 plus h. So what is h? H is the value I added on to 1. That's important. H equals the amount added to 1. Okay. So then we said, okay, we're going to derive a formula. So we went to our average rate of change formula. We plugged in this 1 plus h minus s of 1. S of 1 we already knew. We had 1 plus h minus 1. That's what that y2 minus y1, x2 minus x1. We noticed the 1's cancel. We got to this formula here. And then I said, hey, let's check our answer with the previous known work. That is always good to do, right? That's where we checked it. Now, what was h again? H was the amount we added on. And when we went to this formula here, and let me get to this formula again, the average, and it really was the average on 1 to 1 plus h was minus 16h plus 64. Okay, now we found the average. We had a known value from 1 to 1.1. First thing I want you to do now is figure out what h is. Yes, in the back. What's your name? Because you came in late, so I will do this. Sorry. It's Caleb. 0.1. And what did I use last class, Caleb? 1.1. And that was my mistake. And it was right, well, first off, it's always good to get your mistake out early in a semester. So that's off my checklist. And so it would have been, h would have been 0.1, and I used 1.1 in the calculator. So that becomes minus 16 times 0.1 plus 64. And that is minus 1.6 plus 64. And that is 62.4 if I did that right. And remember, you can use your calculator. I was born long before calculators, so I have skills that they don't teach anymore. And was that the answer we had from our previous work? 62.4. Let's go back up here. 62.4, does that make us happy? It does, right? So that makes us happy. See, there's a happy face. And why does that make it happy? Because now we derived a formula to help us figure out the instantaneous velocity, and it already matched up with some previous work. So we feel good about that formula. Okay, so now what happens? We need to look at what happens as h approaches 0. So let's get out our calculators again. And let me get out a calculator. We're going to go back to our table. It's already open. And before I do that, though, I wanted to point out, why can't we just plug h0 into that formula now? Well, we got to remember how that formula was created. So let me go back real quick. Why can't we just say, we can put in 0? Well, this formula was really from here, and we can't put in 0 there because the first commandment in my class is thou shalt not divide by 0. And so, and the second one is thou shalt not take logs of negatives. All right, so we can't directly put in 0, but we can put in something really close to 0. So back to our table now, and I'm going to go look at my table again, and we should have a minus 16x plus 64. I'm in the table setting, and then I'm going to go ahead and hit enter, and start at 1. I like to have it on that ask equals x, so I'm just going to keep hitting enter, enter, and I always mean to clear out my calculator, but I never do. Let me just delete. All right, so let's start off with an h close to 0. Let's build just a little bit of table here. H, the average from 1 to 1 plus h. Well, we already put in 0.1, so let's go ahead and rewrite that down. 62.4. Let's move in a little closer. What's smaller than a tenth? How about a hundredth? So let's put in 0.01. Hit enter. And what is that? That is 63.84. Everybody with me on these values? All right, I'm going to go to large screen here. All right. Yep. Oh, we don't have that yet. So sorry, we don't have the D word. So I forgot to ask, how many of you have previous calculus experience? Yeah, so you have to kind of hold back a little bit because we like to lay in the theory. And high school calculus classes often don't lay in the theory, so we lay in the theory a little bit more. So we'll get there, though. I trust me on that. So, all right, so let's put in what's closer than 100? About 1,000th, 0.001. Put that in real quick. 0.001. Hit enter. And that is 63.9840. What's closer than 1,000th? How about 10,000? 0.0001. Let's put that in real quick. 0.000 zeros and a 1. Hit enter, and that is 63.998. Okay. I want you to make a conjecture about the instantaneous speed at t equals 1, and I want you to look at the table when you do that. What do those values look like they're approaching, class? 64, right? They look like they're approaching 64. So what would our conjecture? And a conjecture is a educated guess what you think is going to happen. We didn't prove it, though. That's coming up with the derivative and all that stuff. But we got to take steps in there. So our conjecture is the average or the instantaneous speed is 64 feet per second. But that's a conjecture. What's a conjecture again? An educated guess based off of some facts. Okay. So that is section 2.1. And 2.1 is just kind of an introduction to kind of what's going on here. And we're going to be looking at these type of things here. So you know what happens, seeing here is we got to have some terminology for this. And so that's where we go to section 2.2. So let me start a new page here. Oops, wrong keyboard. Okay, so section 2.1 was all about kind of helping us understand we're interested in how things are changing. And things change differently. We saw that particle, that rocket speed was slowing down, so it wasn't at the same speed. And we like to be able to figure out how can we tell when that rocket hits its max height. Well, if you notice, what was its speed at the max height? It's actually 0 right then. That's why so we got to have some tools available. All right, so let's put our first big definition up of the day. For some reason I do not have this section in my notes. So definition. And this is called a limit of a function. And this is what this author calls, I can't spell that word anyway. It's a rough definition. This is not a precise, we can use this definition to do rigorous mathematical proofs. But we'll get there eventually. All right. Suppose the function f. So in case you haven't been in my classes before, I know how to spell function, but we write it so much, FNC, this function. So we got a function, we call it its generic name f, is defined for all x near a except possibly at A. Let you copy this down. Okay. Raise your hand if you're near me. I mean, so I could hit every one of you with a spitball, so aren't you near me? Near is kind of an ambiguous term, isn't it? So that's why this is a rough definition. Near is undefined. What is near? Later on, we'll call it a value, a very small value. We'll call it epsilon. But for now, near is close enough. Even Mark back there, I could get you with a good spitball if I had to. I was really good at middle school. So, all right. All right. Now, if f of x is arbitrarily close to L, as close to L as we like, for all x sufficiently close but not equal to A. We write. Okay, I'll give you a chance to get this written down. That's good. We're just missing one today. And just a reminder, it doesn't bother me if you show up a couple minutes to class late. That happens. If you make a habit of showing up like 15 minutes late every class, then I'll talk to you. Because that's just rude. Unless I know it's for work. Okay, so first off, if you look over here, we have lots of ambiguous terms. Arbitrary close. Well, that's not a precise definition. Sufficiently close. That's why this is called a rough draft. Later on, we can assign variables and tie it together. Okay, so let's put on a couple. We got to finish this definition. So this is what's going on. It's saying, hey, we got a function. It's defined, so it has input, output values for all the x's around A, except maybe at A. And as we're going into A, we're close to a function value. All right. And that is, I don't know about you, that's way too much to write. I mean, think about being Bart Simpson and having to write this 1,000 times after school. It's going to take him forever. So what do? We invent some notation. So this whole paragraph here is reduced, and mathematicians were probably the original text speakers, is reduced to the following. The limit as x approaches a of f of x equals L. And you want to read that as the limit as x approaches a equals L. So this sentence here, and this is a mathematical sentence. How do I know it's a mathematical sentence? Because there's an equal sign. That's the verb. So that mathematical sentence there basically says that paragraph. We will get to the formal definition. Oh, I don't remember which section in this, in chapter 2. So, all right. So when we see this, what do we know? Well, the function has to be defined around A. A itself could be a whole or something like that. And the function values have to get really close to L. Okay, so finish copying that down, and then we'll move on to looking at this graphically. All right. Well, you've been sitting now for like 25 minutes. Why don't you stand up, stretch real quick, and then we'll get into this topic. Take like a 5-minute break. Talk to somebody. Do your Snapchats. You want to do it? Well, it's not a tweet now. What is it? What do we call it? An Xy?
X.
An X. You want to X? Feel free. What do we call if you thread? Anybody know what that's called? I mean, Twitter was you tweet. Now then my show I was listening to this morning, they couldn't figure out what to call tweets now. And I have thread, but I've never actually posted. But what do you call it? If you post a thread, is that a threader? Come on, young people, you're supposed to know this stuff. Help out the old guy. Are you Googling it, Marissa, so we can find out what it's called when you post a thread? It's probably not been decided yet. And it doesn't bother me if you use your phone in class. So I forgot to load my graphs up. So we're going to be... I lost my Surface Pro died last year, so I got a new one, and not all my workbooks transferred over. All right, and I missed it. I didn't have these graphs. So we're going to have to suffer through some drawings. All my drawings are perfectly drawn. That's not bad. Okay, so let's look here. First off, it has to be defined around some interval of A. So if I take an interval around here, if you take an X here, does it have a Y value up there? It does, right? Take an X over here, there's a Y value there. Let's say, for instance, and I'm not going to erase it, let's say there was a hole over there. Well, as long as we can get close enough around A that we miss this hole, it's still what? Defined around A. So that far hole over on the left doesn't matter because I can get close enough. You see, if I'm an X value in this interval here, except at A, am I defined to begin with? I am. Now, is f of A defined? Yes, it is. Okay. So now let's look. As we go into A on this side, oops, got to have a pencil. As we go into A on this side, well, what's happening? We're going into those values there. Is that approaching some Y coordinate? Well, it looks like it's approaching what? This Y coordinate there. As we go in from the other side, does it look like it's approaching that same value? It does. It doesn't matter. Let's say this is, let's say here is f of A. It doesn't matter that f of A isn't in there We're just want to know what's happening as we're approaching those values, not what happens right at that value. So would we say the limit as x approaches a of f of x equals L on this one? We would. We would say the limit as x approaches a of f of x equals L on this one. Okay, let me change this graph. I'm going to change this graph. Well, actually, go ahead and almost, all right, I'm going to change this graph. So get that finished, and then I'm going to change it real quick. You're going to have to keep up with the changes. Are we ready? Are we ready? What did I do? Now A is not defined. Does A have to be defined in that definition? Go back. Let's go back to that definition. It said the function had to be defined for all x near A. That was that little interval, except possibly at A. So you could have a hole at A. You could have a hole, and you could even have what? A jump. But as long as those function values are still going into that same y coordinate, the limit is that value. Doesn't matter what happens right at A. All right, our next picture. Here's A. This is y equals f of x. This graph here, the whole thing. First off, if we take a little interval around A, is the function defined for all those x values? Yeah, everyone has a point, right? Everybody, that's what I'm meaning there. I take this x right here, it has a point up there. It has a y coordinate. Okay, as we go into A, trying to get this a little narrower. As we go into A on this side, what's happening to those y coordinates? Well, those y coordinates are what? Approaching this value. Let's just call this value y1. As we approach A from this side, what's happening there? They're approaching what? Those y coordinates. We'll call that y2. Is y1 and y2 the same value? They're not the same value. So what would we say on this one? We would say on this one, the limit as x approaches a of f of x, and let's call this first y value here L, does not equal L, because what? As we come into A on one side, it's going to one value, and we come into A on the other side, it's what? Going to a second value. All right. Our next example. Let's look at, let me just draw another one here. Let's say this is A. All right. And let's look at this one. First off, can we get some small interval? And it just has to be a small interval. It can be as big as you want, but as long as we can get a small interval, so let's take a small interval around A. So I'm looking at all these x coordinates there. If we come up and find their points on the graph, what would that look like? It'd look like what? This piece, what? Right there. Those are the actual points there on that graph. Now let's look at what happens as we go into A. As we go into A from this side, does it approach the same y coordinate as we go into A on that side? It does, doesn't it? So whatever this y value is, and let's say this y value is 3, and this is the function f of x, and let's even change the A, let's change the A to 7, just for notation now. So what would we say on this one? We would say on this one, the limit as x approaches what value? The value 7 of f of x, and what would we say that limit is? We'd say that limit is 3. And I forgot to draw, if you correspond these over to here, you'll see they correspond to that little piece right there. I always forget to draw that little piece. These would have corresponded to this piece And these would have corresponded to this piece, and it's this gap right there, the reason why that limit, doesn't exist. Okay. So let you get caught up on these. All right. We often refer to this limit as a two-sided limit. The limit as x approaches a of f of x equals L. That's called a two-sided limit. And why is it called a two-sided limit? Because we come in from the left and we also come in from the right. So if we think about this, here's our A. We have some interval there. This side we're coming in from A from the left, and this side we're coming in A from the right. So we need some notation because we don't want to write left and right a bunch of times, right? So we need some notation here. And so this side here, let's pick on the left side. Left side here. I'm coming in from the left side. Are the numbers smaller or bigger? They're smaller, right? So they're coming in from the negative side. So this would be x approaches a from the negative side. We put this little negative as an exponent. And this one here would be as x approaches a from the positive side. Oh, by the way, so that those that can plan, some of you can plan ahead. I know some of you work and stuff like that. The Friday before Labor Day, we will not be meeting because I have to go out of town for a wedding. So that's just my classes. It's not anybody else's classes. They did not give me the power to cancel school for everybody. I had one student thought I canceled school, all of his classes one time. So that's why I always say that now. Wait, Newberg said there's no school. It's like, I said my class was not meeting.
We have Monday off too, right?
We have that Monday off as well. Yep.
Oh, we do?
Yeah. So how many of this is your only class on Friday? Yeah. So Brian gets a 4-day, 5-day weekend because we don't meet on Thursday as well.
And I'm not going to work Friday either.
Hopefully you're going to have fun. But, okay. So, all right, let's put this up here. So we have a right side limit. So these are one-sided limits. And what's a right-sided limit mean? It means the limit as x approaches a from the right side. And remember, the right side on a number line, here's the positives, here's the negatives. That's why we use those two notations. And of f of x equals L. Well, this means you only have to get arbitrary close to that L from the right side only. And then we have the left-sided limits. And that would be the limit as x approaches a from the negative side of f of x equals L. So we only have to approach from one side. Okay, let you get those copied down, and we will draw a couple of graphs here. Okay, so let me draw a graph right here. Here is, let's make this 5. I'm going to do some numbers now. Let's say we come in, we'll make that close. This value is 3. We'll come up here. That is an open point. To make it a function, we'll make that 4. And this is the graph of y equals f of x. So from those that took college algebra, this is what a piecewise defined function. So those that have had me before, and I emphasize piecewise defined graphs because I knew you're going to need to be able to understand them in calc. Okay. So let's look at the following limits. Let's look at the limit as x approaches 5 from the positive side of f of x. So we got to come into 5 from the positive side. So the positive side means what? Out here. Remember, that's off to positive infinity. Need a stick. Nice thing about teaching is I've dislocated my shoulder so many times. Getting back and having to use my right arm, I'm breaking through a bunch of scar tissue. Oh, I was so sore last night. So we're coming into 5 from the positive side. That means we're coming into this x value here. So as we're coming into 5, where are all these y coordinates going to? It looks like, well, that should look like they're going to what? 4. So what would I say the limit here is? I'd say the limit here is what? 4. Then if we look at the limit as x approaches 5 from the negative side of f of x. So now we have to come in from the negative side. Remember, negatives are off here. So we're coming in on this side. What's happening in the y coordinates? They're getting bigger, but then what happens? They stop, and what value are they at? They're at the value of what? 3. So the one-sided limits exist. But if we were to ask you about the limit as x approaches 5 of f of x, well, what's the problem? If you say it's 3, well, those are outside that value. If you say it's 4, those are outside that value. Because one side is going to 3, one side is going to 4, and you can't get 3 and 4 close enough to be the same number because they differ by 1. So what would we say the two-sided limit is on this case? D and E does not exist. D and E is pretty standard mathematical language for does not exist. So I imagine your high school calc teacher used D and E as well, right, Caleb? What's that, probably?
Probably.
You don't remember? All right. Who was it? You don't remember your teacher's name? Okay, you bonded so well with your high school calculus teacher? I can tell you, my high school calc teacher in 1983 was Mr. Claire Dirks. So, I couldn't tell you any of my other high school math teachers, but I can tell you my high school or any other teachers. All right. So it is possible the limits don't exist. Okay. Let me see. Okay. So now, I'm going to use projector 2 for our graphs, and I'm going to write on projector 1. Okay, so let's take some functions now. And our first function I want to look at is f of x equals x cubed minus 8 over 4 times x minus 2. Let's look at this function here. What x value can't we plug into this function? Where is this function undefined? Well, 2, right? Thou shalt not divide by 0. So we already know x cannot be 2. So the most interesting question for us would be, what is the limit as x approaches 2 of f of x? Well, we don't have a lot going on right now other than what? Our definition, which is a rough definition, and what? Graphs. So what do we need to do? We need to graph this function. So over here, when we need to do graphs on our homework, if you want to use your TI-84s on the homework, that's fine. If you don't want to buy a graphing calculator, I recommend GeoGebra. We're going to be using it anyway for our projects, and it does a better job. GeoGebra, by the way, will load on your phones. It will load on any device you have, even if you have a Linux device. You have Linux? No, I haven't ran into a student on Linux for a long time. So, is this still used?
Very rarely.
Yeah. So, I never learned Linux. I was always going to, and I'm glad I didn't. I learned Pascal. It's not used anymore. I learned Fortran, barely used, I think. and a couple other obsolete languages. So, all right, so let me type this function in. And in GeoGebra, it's really simple. Just type it in like a function, f of x equals, and then I need a fraction, so I hit the slash first. It gives me the fraction first. It keeps it a little easier there. And then I do an x, and the caret key is the power. So that little caret key that looks like my and is the power. X cubed, toggle out there, minus 8. And then go down to the denominator here, and it was 4 times x minus 2. Okay, so here we have this graph. All right, so now let me go ahead and show you if I try to put in 2. Let me show you what happens when I put in 2 into the function. And I can type it in just like you would on paper, f of 2 equals, and what do you see? Question mark, it's undefined. If we were to zoom in, we would see what happens right at x equals 2. There's actually a hole there. Problem is, technology doesn't have the ability to show holes yet. I'm waiting, you'd think somewhere along the way, some computer programmer is going to add that feature in to GeoGebra. By the way, this is a worldwide consortium of mathematicians, programmers, federal funding grants to make it the most robust free math software out there. So, but let's look at what happens as we go into 2. Well, first off, let me put a point on there. Now, the cool thing about GeoGebra is, I'm going to turn over this side too. The cool thing about GeoGebra is you get algebra and you get geometry stuff. You get your algebra stuff up here, and then you get some geometry tools in there. So I'm just going to click on Tools real quick. And I want to find a point on the object. So sometimes you got to go to More, and I'm looking for a point on the object. Point on the object right there. Click on it. Put a point right there. Okay. Now, let me go ahead, and I should be able to build a table, but it's going to take me too long. Let me just go back to algebra here. And when we're talking about function values, are we talking about x coordinates or y coordinates? What's the function values? Are the x's or the y's? The y's, right? The inputs are the x's, the outputs are the y's. That's the function values. So I'm really interested in the y coordinates of this point. So I'm going to go ahead, and it always takes me a second. I'm going to type y of a, and what does that do? That now gives me the y coordinate at this point. So what do we got to do? We got to go into x equals what? 2. So let me slide it there. As we're going into x equals 2, what do those y values look like they're approaching? 2.492, 2.565. I know it's a little small there. What do they look like they're approaching, class? 3, right? And if we come in on the other side, what do they look like they're approaching? Also what? 3. If we get right at that value, what happens? I got right there, what happened? It's gone, right? Because it's undefined. We don't care what happens as we're going in. We care what happens as we're getting really close. So just by looking at this graph, what would we say this value is? 3, even though f of 2 is undefined. Now, what if I define f of 2? What if I say, okay, I'll just make f of 2 a point, 2, 5. So there's the graph. Do we care what happens right at the point? No, we only care what happens as we're going into the point. So would that limit change? Not at all. It'd be the same limit. All right, next function. I'll just turn these off. Okay. G of x equals slash. And our numerator is going to be 2x squared minus 6x plus 4. And then our denominator is going to be the absolute value. Okay, and before I type this in, I want to let everybody caught up. And then GeoGebra is one of those that's really intuitive. Absolute value. What does absolute value begin with? ABS, right? Absolute. So I want you to watch right here. So I've typed in the numerator, and I use the caret from the power, and I need an absolute value here. So I'm going to type in ABS, and I want you to watch what happens on the screen here as I type it in. ABS, and notice it used to be black, but they made it white. It popped up here, ABS, and if you click on that, it'll tell you what it is. And sometimes there's more than one option. There's not a lot of things that begin ABS of X. Well, that's what I want. And now I got to type in what I want inside that absolute value, X minus 1. All right, so here we have this function. Oh, did I hit record today? Sure. Yeah, I did. All right. So here we have this function. Let me just kind of draw it in my notes here, rough draft. And looks something like this. And right here at 1 is undefined. Why is it undefined? Because thou shalt not divide by what? 0. That would make the denominator 0. So it's undefined at 1. F of 1 is undefined, or you can write does not exist. Both work for me. Okay, so what would be our interesting question then? Our interesting question would be, what is the limit as x approaches 1 of g of x? And I called this function g. Okay. And then the second question would be, what is the limit of g of x as x approaches 1 from the positive side? And what is the limit as x approaches 1 from the negative side of g of x? So I want you to spend a few minutes and look at those yourself there. I'm going to turn the graph on both sides just so it's a little easier for this side to see it. By the way, sadly, this is the last semester of this classroom. I'm going to cry at the end of the semester, just to warn you. It's my favorite. Of almost 40 years of teaching, I've never taught in a classroom finer than this classroom. I even got my own closet. Yeah, you know how hard it was to get a closet on campus? I had 3 children, but now I only have 2. I traded one in for the closet. Yeah, the health science we're adding on. So if you're nursing, it's really good because they're adding on a nursing through this area. There might be a hot deal on a 1-ton coal cart out there too. If anybody's looking for one. All right. I guess I see you still thinking there. Thinking is always encouraged. So let's start with the one-sided limits real quick. So let's start first off with, I guess I don't need my stick. Let's start off first with the limit coming from the left, from the negative side. So as I come from the left on the negative side, I'm coming on this side here. So what's happening? We're approaching those y values, what, right there? And I didn't put it on my picture, but we can see it on the graph there. And on the graph over there in GeoGebra, it looks like, what, 2, right? All right, so what would we say this limit is? We'd say this limit is, what, 2. Then let's do the limit as we come to 1 from the positive side. So coming in from the positives means this side. Where are those y values going to? They're going to that y value there. And what was that y value over there on the GeoGebra drawing? What? -2. So that is what? minus 2. Are 2 and minus 2 the same number? No. So what do we conclude about the two-sided limit? DNE. And we'll have that as a theorem later on. The one-sided limits have to agree for the two-sided limit to exist. So this one would be DNE. Why is that? Because this side goes to 2, this side goes to minus 2, and you can't get them arbitrarily close. You say, I'm going to stay within that. Well, what's the problem? The other side's below that. You say, I'm going to stay arbitrarily close to minus 2. What's the problem? The other side's above it. So you got to stay close to that limit. And so that one's DNE. Okay, one more function today. All right, really quickly, those that all have had trig before, graph this cosine 1 over x. Now that was a joke, because that 1 over x messes with you. All right, first off, what x value can't x be? 0. So what's probably the interesting limit to look at? The limit, and let's call this a function, let's call it h of x. The limit as x approaches 0 of h of x. And we might even be interested in the limit as x approaches 0 from the positive side, and we might look at the limit as x approaches 0 from what, the negative side. Unless we look at the graph, we can say it all together. So, all right. So this is an interesting graph. I'm going to let everybody get caught up before I graph it. Those that eventually take Calc 2, this will be we'll look at this graph later on as well. Okay, so let's get a look at this graph. So I called it h of x. I could just type y equals 2, by the way. Equals. So how do you think I get cosine? COS, right? And I type in cosine, and you see with COS, there are a lot of cosines. Functions that begin with COS. So you might have to peel out which one of those drop-down menus. But cosine by itself, and then I just do a parenthesis, that got me the cosine. And then it's what? 1 divided by x. All right, so there's the graph of cosine 1 divided by x. All right, I'm really interested in what's going on right around here. So I'd kind of like to zoom in on that. And I don't really want to make the y's bigger. So I'm going to go back to my tools here. And I'm going to come up to the top here. And let's see here. Where was it? Oh, move graphics view right here. This one here. And I'm going to grab it. And I'm just going to click and make it. Oops. Grab it. Make it so I can just stretch out the x-axis. So we really get a look at the x-axis. What's that kind of looking like now, class? Kind of a spring there, right? Okay. So now, I want you to make a conjecture yourself before we go through this. So make a conjecture. What do you think these limits are? Based off of that graph right now. So write your conjectures down. Good graph, isn't it? By the way, these little things here are just hiccups, because how does they graph these functions? They don't memorize the graphs, they just plot lots of points. They're just super fast at it. So these are little hiccups because of the sampling. I could increase the sampling, but this classroom computer doesn't have the power. At least once this semester we'll play, let's mess up the classroom computer and see if I can jam it with too much calculations. All right, everybody have their conjectures? Now I want you to stand up and go explain your conjecture to somebody else in the class. Get another stand up, bounce ideas off of each other. I'll give you a couple minutes to do that. Everybody stand up. Go discuss your ideas with each other.
I don't know. It's like you choose each one. I don't know.
Pretty impressed you're going to use geography, by the way. Okay. That's a wonderful program. The geometry package is amazing.
Yeah. But it shouldn't come in at zero though, right?
Yeah.
All right, then sit back down. Anybody want to share what they think the answer is? So I'm glad you pointed this out. What was your name again? Magnus. Magnus? Magnus, all right, yes. All right, can a limit have two answers? Well, let me go back to our definition here, and let's go back to our informal definition. That would have been a better play there. Does it say, it says what? 1L. So we can't have two answers. All right. So -1 and 1 are not the possible answers. All right, anybody want to go farther now? Based off of what Magnus just said. Is that? It does not exist. What happens is on this one, and if you think about the graph of 1 over x, that's the composition. That looks like this. So as x is getting closer and closer to 0, what's happening? We're running around that unit circle more and more. So what's happening? They're running around that circle, and cosine's what the x-coordinates is going from what, 0 to 1 to -1 to 0 and back and forth. So the -1 and 1 happen. So if I zoom in here, we'll see how much, maybe it's today's the day I play, lock the computer up because it doesn't have enough power. But as we zoom in, what's going to happen is, and you already see, we're starting to get now it finally had caught enough power over there. It finally got enough samples in there. What happens? It just keeps oscillating back and forth, back and forth. This left-hand side of this graph, you can't tell it, is actually not even connected to the right-hand side. Right there at x equals 0, the two graphs don't exist. And because, I don't care, you say 1, well, I can bounce up to, you say -1, I can bounce up to 1, and you take an arbitrary close. So let's say I want to stay within a half. Well, 1 is not in a half of -1. So this one does not exist because it just keeps bouncing back and forth between -1 and 1. You say 0, well, you got to stay within arbitrary close. So make it a half. Well, 1's bigger than a half. So this one is a big fat DNE on all of those. Now the interesting thing is, let me go ahead and type a slightly different version of this. And I'm going to go with 0 less than x less than or equal to 1. Oops, got to type this right. 0 less than x less than or equal to 1. I guess I got my caps locks on. Cosine 1 divided by x. Missing a comma. And let me hit enter. That should be a good function now. Let me turn off this one here. And let me zoom out a little bit here. I don't want to do it that way. Bear with me a second. Let me go back to my tools here. Go back to my graphic moving tool. Slide that over. Let me shrink this scale back down here. Okay, so here, let me just put it over here. So here's a little interesting thing on this one. So here I've just graphed half that side, and I've only graphed it from 0 to 1. This curve here, later on, turns out it will be a finite length if I remember right. The one of them is, even though it's an infinitely long, here we have an infinitely long, is an infinitely long curve in a bounded area. This curve is infinitely long, even though you could bound it. So, something to blow your mind away there. So, all right, so that oscillating back and forth makes it does not exist. Okay, so that concludes section 2.2. And when we move into 2.3, we'll be laying down how to do the limits without having to look at every graph. So, all right, we'll start laying down the foundations. And I don't really feel like starting that next section. So both of these are more intuitive, plugging in numbers, looking at tables, and making conjectures. And then we'll get into the actual, here's the theorem that makes these calculations easier. But that's the next section. And I'd rather not do that until you do these two homework assignments. And you you previous calculus students that have had it, got to go back to the basics on this one. No derivatives yet. We'll get there. All right, thanks for coming to class today. Caleb's still analyzing that graph. Enjoy your 4-day weekend coming up, Brian. So I told you early so you can make better plans too.
There you go. I've got to tell.
Yeah. That's why I told everybody early, so in case you